Welcome to Lecture 8, Recursion and Tree. We are on Chapter 6b, the Part 2 of the Chapter 6, Functional Programming. We'll be discussing in Recursion and the Tree. So in the previous chapter, the Chapter 6a, we talked about the basic concept of the functional programming. And we use the map, reduce, and the filter function to talk about how you apply function to the data. So basically you have map function and you can put a function and apply it to all of the data, and this data can be iterable or some data collection. So it is applying a function as input, also a data as input, and create a new data. That is mapping. And we also have the reduce partial function, and also we also have the so-called the filter function. Okay, several different functions. And in this chapter, we are away from these different topics. So this chapter 6b, we will have 3 parts. Number 1 is talking about the general concept and the rule for the functional programming. Excuse me. Second portion is the recursion. Third portion is a tree. So basically, we divide this into 3 parts. Number 1 is the rule for functional programming. And instead of using the standard function called map or filter or reduce or partial or some other functional tool in the fun tool package, we don't cover it this time. This time we are going to talk about the basic rule of the functional programming in Python language and how to use it. And second part, we talk about recursion. So recursion is usually the way that we actually use the functional programming, because when we try to work on the data structure, say an array or a tree, you will need to use a recursion if you don't want to use a for loop. And then last one, we talk about tree. So tree is a data structure, and we'll apply recursion on it. And this whole thing is actually an example of the functional programming. So basically, we are still discussing the functional programming, but we will look into the way that we use functional programming. So this chapter is focused on the application of functional programming and using the functional programming key concept of the recursion onto the data structure. So it is basically mostly on the application of functional programming. Okay, so 3 main parts. Part 1 on the technique of the functional programming, part 2 on the recursion, part 3 on the data structure. So the beauty of functional programming. What made functional programming a viable choice for artificial intelligence project? The most common programming language currently used for AI machine learning are Python, R, Scala, Go, and some other language. Okay, so we picked Python for this course for programming language, the structure and the interpretation of computer programs, because Python has the feature of functional programming, object-oriented programming, and the traditional imperative programming. So it presents a very good example. But we also will teach you the scheme language that will be in the chapter 7, or we will, or I call it lecture 9. We will talk about scheme language. So basically, that is one functional language we'll talk about. And we primarily use Python because Python is a good pilot language that covers the so-called imperative programming, object-oriented programming, and functional programming. And they own enough hardware and software advancement back then for implementations. Some commonalities in all of above language options are that they are simple to understand and to promote clarity. So some languages are invented just because of educational purpose, and very few of them are actually popularly used. So right now we would say this Python, Julia, R, Scala, these are more popular programming language for functional programming, and also Go, okay, in the machine learning field. Okay, others not that popular. So functional programming features, before we see functional programming in machine learning context, let's look at some of its characters. Functional programming features, immutable. Immutable is a very important feature of functional programming. If a variable is declared and used in the program, the value of the variable is never changed later anywhere in the program. We call it immutable. Each time the variable is called, it will return the same value assigned originally. This makes it pretty straightforward, eliminate the need to sync the state change throughout the program. So functional programming, we really like to have such things. We have a function f and pass into function g, pass into function h, and may do recursion, calling itself, okay? But the data, actually, they want it to be in, say, x, okay? You pass through it, and then this one, x may be modified, and be modified again. But this variable and then this variable are two different variables. So for x, if you refer the x to anywhere in the functional programming process, it is the same x. We make the variable immutable. That is the idea of the functional programming, the first feature of functional programming. Try to make the variable to be immutable. But in the scheme language, we do have the set function, okay, that will store some value to the x. Yes, we do have that. In this language, we do have setQ variable, a function, okay, and this make the program with the state. These are for the practical meaning, but original idea of the functional programming do not require such thing. Okay, referential transparency. This means that an expression or a computation always result in the same value in any part of the context. Okay, expression or computational result of a expression. Okay, okay, a referential transparent programming language program can be manipulated as algebraic equation. This only is when you reference a certain part of the expression or computation, the result should be the same, okay? And we can, if you have such a feature, then we can manipulate the language in the algebraic equation. So you can actually combine the different expression and computation, and anywhere it will deliver the same result. We call it referential transparency. Next one, higher order function. Higher order function means you have a certain function, you can pass another function into it, and then you may generate another function and then pass to another function. So using function as parameter or return value, we call it higher order functions. So a higher order function can take one or more functions as arguments. They may be able to return a function as its result. So higher order function means that you can take one or more function as arguments, and then you can return another function. So higher order functions are useful for refactoring call or reducing repetition. What is refactoring? Refactoring means you have certain part of the call, and then you try to share or try to extract certain part of the code to another part. Okay, that's called refactoring of the code. This example, let's see. We may have some multiply and add function. Okay, and if your function can be passed to the other, then it can be reshaped. So let's look at this refactoring of the code. So here, let's actually create some program refactoring the py. Okay, so let's assume that we have a function. This one is defined. Okay, accumulator. Okay, accumulator. Okay, so you actually has the x. Okay, let's actually have the x. Okay, and this one you actually will pass an x to the program. Okay, so you will return the result of this one. So it actually may have two values. Let's assume that the two value is actually a and b, two coefficients. Okay, a and b. So you will this one you will return. Okay, you will return a times x plus b. Okay. So here, let's assume that we have a equals 1 and b equals 2. Okay, so we try to print. Okay, this accumulator. Okay, of 1 and 1 and 2. Okay, I'm sorry, a and b. Okay, so this one accumulator. I'm sorry, here I have a wrong spelling. Okay, so something like this. So this is one function called accumulator, and we run it and we will get a result. So far we actually get, okay, let's see. We print it, the result is a times x. Okay, let me see. How comes that I did not get the result? I have the return value accumulator x a b. Okay, x equals 1. Let me save it one more time. Wrong. So I got 3. Okay, I got 3. So this one is, I do have, okay, I do have, here I do have a function accumulator. Okay, and I pass 1 into there. And this one, basically the value of this one, it will pass the value into here. So the 1 will be multiplied by a, okay, and then it will plus with a b value, okay, with a b value, and it will deliver the result. Okay, it will deliver the result. It deliver the result. And we may apply this function a few times, okay, a few times. So let's assume that actually we try to do this, okay, try to do this. So we start with this, okay, and let's assume that we actually do this one for, okay, for x in range, okay, 1 to 6, okay, and actually it's from 1 to 5, okay, and then we'll do the following step. Okay, we will actually do calculating this factor. So my new x will be this one, okay, and every time I'm going to print my x, okay, and at the very end, let's see here we have the x, okay, and the final result, okay, final result is have the sum equal 0, okay, and every time we actually assign the sum to the current x, okay, and at the very end we actually print out the final sum. So, okay. So initial value is 1, okay. So you pass in the 1 and you print it and 1, calculate with the new value. Okay, let me see. This one, every time we actually want to get a value, okay, and then we accumulate. Okay, this one actually, let's put it to our sum. Let me see. Okay, here that's actually, no, here I have some trouble. Okay, so this one is, we do have times and actually plus. So we pass x into here, we have variable a and coefficient b, and we pass the value to here. Okay, and the result we will actually, okay, this one actually initially is 1. Okay, so basically this one's 1, and the value is actually not going to be passed. So let me multiply it a little bit. Okay, here, let me multiply a little bit. So here, let's see. Let's actually have the index I equals 0. Okay, so here let's use while I less than 5. Okay, 2 pi time. So 2 pi time and I plus equals 1. So we do pi time of these. Initially, let's have our sum to be 1. Okay, let's call it x now. So I'm going to print x, and okay, and eventually the result we will put into there. So we will multiply and accumulate for actually 5 times. So this one initially we get 1, and if we into there, it will become 3, right? So 3 times a is 1, then plus 2, it will become 5. Okay, so this one it become a odd number sequence. Okay, it becomes an odd number sequence. So this one is a function called accumulator function. Okay, so this accumulator function is one function. Okay, so we can do refactoring. Refactoring that every time we actually multiply and add, so we can have a function okay, and this one would get x and a, okay, and we will return actually. So here we will return a times x. Okay, this is what we will have. Okay, so this one will get some result. Okay, and we return it. And we have another function called f function. This one would be a, x, and b function. Okay, and we'll return. This one is x plus b. Okay, so the x number keep there. Okay, so that's actually we do it one more time. Okay, and let's put it over here. And here that has a print function. Okay, so I will print the value, and every time I'm going to do this, I'm going to multiply. Okay, and the result of this guy, I'm going to use it, okay, for the adding function. Okay, and let's actually copy this one and put it over here. Okay. Okay, so that's that. Okay, so we have one thing, we use one accumulator. The other one we do factoring out some operator. Okay, factoring out some operator. So we make it in this way. Okay, so that's actually wrong. Okay, so the result is the same. Okay, so factoring of the function means that the part of certain function being factored out. Okay, being factored out. It's just like you have x squared plus 2x plus 3, and we make it x plus 2. After that, multiply with x plus 1. I'm sorry. Here 3. Here actually is 2. Okay. It is similarly like this. Okay. Here we are factoring the expression. Okay. And right here we are refactoring the function. Okay. Refactoring the function. So we factoring out some part of the function into another function. Okay. That's called refactoring of the function. So that's the refactoring of the function and reduce repetition. Okay, reduce the repetition is another important issue. Okay, so map function found in many languages, example higher order function. Okay, so higher order function means what? You refactoring. So originally you have accumulator function of the x. Okay, with certain variable a and b. Okay, so now you break it into multiply, okay, accumulator. I use AC, okay, of x and a, and then here we have the so-called f function. So it's a refactoring, okay, and reduce application means that you can pass the function to the map function. So that's another feature, okay. So these are the passing the function to another function is a example of higher order functions. Okay, so what kind of programming is good for AI development? Machine learning is a subdomain of artificial intelligence, which deal with the concept of mapping predictions from data, taking action without being explicitly programmed. Okay, recommendation system and so on. Any programming approach that focuses on logic and mathematical function is good for artificial intelligence. Okay, artificial intelligence. Typically, we talk about artificial intelligence. Typically, we talk about a few things: natural language processing, okay, vision, okay, and then speech recognition, okay, and then OCR, okay, OCR. So these different things, really, they are doing what? Doing pattern recognition. So that means that when I write an A, you try to understand that is a stroke of A, that's computer vision, okay? That's computer. So pattern recognition is one of the feature, okay, one of the function for AI. So machine learning use the past experience to deal with the pattern recognition. So machine learning means, okay, I got a handwriting, say, like this, okay, handwriting like this. I'm going to match against my historical data. So here I have a database of different way to write A, okay, of different way to write A, and I'm going to try to actually match whether it's A or not, okay, and I do have other character like B, okay, beta, whatever, okay, and that is a pattern recognition issue, okay, it is a pattern recognition issue. So right here, okay, right here, we can apply different mathematical function to it. Okay, so say age detection, we can detect the pattern like this. Okay, okay, and that age detection is actually providing some mathematical functions. Okay, some mathematical functions. So basically, your characters fit in, you actually do age detection. Okay, age detection. And it create the edges, okay, the edge features. And we use the edge features to determine whether it's an A or not, okay. So the logic and the mathematical function are good for the artificial intelligence. So functional programming, which can be decoupled or factoring out the different stages of the artificial intelligence, okay. So it's good for AI programming. So once the data is collected and prepared, it is time to build your machine learning model. Okay, this typically entail choosing a model and then training and testing the model with data. Okay, so we talk about it for the OCR. Once the desired accuracy and the result achieved, then the model is deployed. Okay, so you keep learning. Okay, keep learning your database, keep accumulating different word for A. Okay, keep doing that, and you do keep writing. Okay, getting more data and train your model and improve the accuracy of the prediction. Okay, increasing the accuracy of the prediction. Okay, and that will help the AI. Okay, that will help the AI. So for AI programming to work well, a language needs to have the low-level implementation of faster communication. So basically, being able to communicate with the processor fast, that actually is important. Okay, this is why many machine learning libraries like C++ achieve faster performance. Object-oriented programming with mutable object and object creation is better suited for high-level language development, but not for AI. So OOP is not for AI. So basically, we look at the different computing paradigm. OOP more suitable for window or event-driven programming. Okay. So functional programming, instead, pure functional programming, it is okay for AI, good for AI. Okay. And because it's all which data are immutable, okay, immutable. So you can pass the data and function quickly through the evaluation. Now there is another issue right here is the processor, okay. So at this moment, we do see some vendor like NVIDIA that support the the graphic processor, okay. We do see Google provide the tensor processor. So from the processor improvement, we can see another order of help for programming language to make them more suitable for AI developers. So as AI is heavily based on math, languages such as Python, R are widely used AI languages. Okay, R rely more towards statistical data analysis, but that support machine learning and neural network packages. Python being faster for mathematical computation with proper support for numerical packages. So Python by itself is better for the tensor, the metric, the tensor processing. Okay. The metric is 2D data. Okay, tensor is 3-dimensional or more data. So Python's numerical package is better for that. So as long as you can have good mathematical support for the numerical package and with some improvement for the processor, then it will be a good language for AI. Okay, for AI. So there are some benefits of functional programming that make it suitable for AI. It's closely aligned with mathematical thinking, and the expression are in a format close to mathematical definition. There are few or no side effect. Okay, so that's a good why we have functional programming and using Python. Okay, it's good for functional programming to do coding, and it's good for AI, and that is the purpose of our course being refocused on the so-called structure and interpretation of computer program, and we use Python as an example to deal with this functional programming. And that's core and more consistency. Okay, functional programming use fewer lines of the code. Okay, so in terms of coding, it's easier. Okay, and without sacrificing clarity, more time is spent in thinking. Okay, so when you do programming, more time is used thinking out the function. Okay, and then when you do coding, the coding is fewer lines. Okay, and execution will be fast if you have good processor support for your functional programming paradigm. And functional programming paradigm is good, okay, just like GPU. So you will get good. Okay, so AI program consists of large solve metric manipulations. Okay, so you work data set in AI with some algorithm to make changes in the data to get modified data. Okay, a function on a value to get a new value is similar to what functional programming does. Okay, it is important for variable and data to remain the same when working through a program. Okay, so right here, what we discuss is functional programming have the nature of less code and more consistency. So it is more suitable for AI. Different algorithms may need to be run on the same data, and the value need to be the same. Immutability is well suited for that kind of job. Okay. So the characteristics and features of functional programming make it a good approach. Okay, make it a good approach to be used for artificial intelligence application. So this chapter we discuss the application of the functional programming. Okay, and we do emphasize functional programming is good for artificial intelligence. Okay, for artificial intelligence, and AI can do without object and classes of object-oriented programming. It needs faster computation and expect variable to be the same. Okay, variable is after computation, so that the operation made the data set consistent. Okay, so immutability very important. Some of the popular functional programming languages like R, Lisp, and Haskell. The later two are pretty old language, Lisp and Haskell. And are not very commonly. Okay, so Python can be used as both. And we do see C++ language also has C++ 20, okay, 1720. They already supported the machine learning and also the functional programming. So basically, it is a good feature, okay, and it will also help Python since Python can code the C language code. So here we have two paradigms, okay? So you can use functional programming in Python, okay? And if you need speed up, you can run the C++ environment. That's one way you can do it. The other way is you may use a Python combined with CUDA or some other parallel processing package. And then you gain the machine support. Okay, you get the machine support. So either way is a good way to deal with the AI programs. And that's the reason why we pick Python as the pilot language that we use in this course. Okay, so Python is the language most commonly used in AI. Okay, and we do show you the Python, okay, and use it as a pilot language. So basically here you have a Python that you can use for core computation if you call CUDA, okay, from NVIDIA, or you actually put onto C++ to speed up, okay. On the other hand, Python also support good GUI, okay, GUI, graphic user interface, okay. It also support good design framework such as internet. Okay, such an internet. And its conversion to JSON is also very simple. So Python as a language, it is good, okay? It is good in supporting AI and also the general purpose programming, okay? And general purpose programming. And we talk about the imperative programming and the object-oriented programming, and now we discuss functional programming, and Python has the good feature for all of these, okay, and especially Python also has the scikit-learn library, TensorFlow, okay, TensorFlow, and PyTorch, okay, those kind of the AI supported projects. So functional programming is fault tolerant, okay, it's fault tolerant and important for AI. Functional programming also has the fault tolerant and the fast for critical computation and the rapid decision-making feature, okay. As of now, there may not be many such applications, okay, but in the future we may have that. Okay. To further understanding why functional programming for machine learning, read the following thing. Okay, you can read somewhere else. Okay. Okay, so powerful programming language for doing machine learning. Here we do see good candidate that actually is R language. Okay, and your Python language. Okay, your Kotlin. Okay, these are Go language. These are actually good languages. Okay, C++ also support functional programming, and it's lower level. Okay, so here we do see different terms, and as a course we pick Python as our pilot language to study every feature of the programming paradise. Okay, progress track for functional programming. So previous section we discussed why we use Python and why we choose Python language for study in functional programming, and because it's linked with artificial intelligence. So in this chapter, I say that we mainly look into the application for functional programming. So now let's look at in addition to the map, reduce, and filter, what other way that Python has can support the functional programming. So functional programming means that you have a function, you can input a data and output the data, or input a function, output a function. Okay, so this we discussed already. And program structure for functional programming. So Python support higher order function, declarator, okay, functional chaining, and also currying, okay, also currying. And these different support will support the support functional programming. In addition to the function tools, okay, function tools are the default map, reduce, and filtering. Okay, here we are talking about the general programming structure that support the functional programming that is available in Python. Okay, so function, higher order function, you can pass function and variable into a function, and you can generate variable or function as well. Okay, so this one we discussed already. And currying is partial argument application with functions in Python. So typical currying is like this. This one is not a Python example. This one is a JavaScript example. So we have an add function. We take A, okay, and then you will return a function object. Okay. So the result of this A function S3, okay, you will return a function that called S3. Okay. You can think about it. It actually will return a function S3. And this S3, you pass 4 to it. Then you will get a result of 7. Okay, you get a result of 7. So this one, we call it currying. Okay, we call it currying. So let's do this. Okay, so let's look at the currying. So here, let's do curry. Okay, curry1.py. Okay, let's do this. So we can have a function. Okay, this function is actually called f function. Okay, so f function we take a and b. Okay, we take a and b. We take a b. So we will return a plus b. Okay, so right here we do print. Okay, f. Okay, a and b. Okay. That is one function. Okay, that's one function. Here, let's actually do a equals 3. Okay, b equals 4. Okay, so let's save this one and let's go. Okay, let's go. So this one we get 7. Okay, we get 7. Not surprising. Okay, so here let's actually print this one. Let's do again a different way. Okay, so here we can define. Okay, add function. Okay, this add function will add a, okay, add a, okay. So here we will actually define another function, g function, and this g function will take an x, okay. So here we can call this one base, okay, base, okay. So base number. So base number, we put it there, and we will return, okay, return g function, okay. So basically, the f function will return g function, okay. So basically, you have a f function you take the base in, and you return a G function, and this G function will perform 8 base feature, okay, 8 base feature, okay. So basically, you perform 8 base feature, but this 8 base feature, it had a parameter called x. So here we return base plus x, okay. So now let's do this one, okay. So we can create a function called s3, okay, equals add of the 3, okay. And then we do print, okay, we do print, okay, add 3 of 4, okay, and print. So S3 is a new function. That's the G that we actually return. Okay, that's the G that we return. That's called S3. Okay, and we actually have a parameter. It's called 4, and we print this one. Okay, so that's that. And we can also do this one. We can also do x equals at 3 and 4. Okay, and we print x. So this x value is actually, we call the S3 function, the create function called that will return S3, okay, and that function we again pass the parameter 4 to that S3 function. So this S3 is a function, okay, and you pass 4 to it. Okay, so this 3 way of doing the same way, they all return 7, okay? They all return 7. So right here, let's call it, okay? Traditional way, okay? And this one, let's call it function, okay? So let's call it, what's that? We create, using the input, we create a function. Let's call function vector. Okay, the function vector. And the third one, we actually call it curry. Okay. Third one, we call it curry. So what's wrong here? Okay. So they all get the same result. They all get the same result. Okay, so that is the curry. Okay, that's the curry. So that's a curry. So you can have a traditional way that you pass in x and y. Okay, you can have the so-called add function or plus function, create a function called plus 3. Okay, and you use a plus 3 function. Okay, to get another parameter. Okay, this is the curry implementation. Okay. And curry implementation, you can have this one, A times B times C, you get D, okay? And you can, if it's curried, the result of A processing B will be, you get the result, okay? Okay, and then pass that result to another function, okay? So you can keep doing that, okay? You can keep doing that, okay? Okay, that's curry. Okay, that's curry. So left side is one way, right side is curry. Okay, left side is the traditional functional composition. Okay, left side, right side is the curry. We'll talk about this later. Okay, more. So there are also decorators. Okay, so decorator is creating a decorator, and decorator is another way to create use the concept of higher order programming, okay, higher order function. So we create a decorator, okay, and the structure of decorator, okay, and chain decorator. So decorator have many issues as well, okay. So decorator, you originally have a function of the yellow apple type, okay, and you are going to create a new function with different features, okay. Decorative features, okay. And functional chaining. Chaining is you have one function, get the result, you pass to another, and then pass to another, and then pass to another. That's called method chaining. Okay. So such as this one, actually you can chain function. Okay. So your hello world, you can put the core inner HTML here. You wrap up with the U tag and wrap up and again by a I tag and wrap up again by a B tag. Okay. That's called chaining of the functions. Okay, chaining of function. And each layer can be using a declarator. Okay. So you have a word method and you try to check palindrome of it. So you actually check single letter, check two letters, and check another layer. So palindrome function can also benefit from chaining. Okay. And here we have neural network processing. Okay. We have value, okay, and weight, and then sum up and make decision. Okay. This is the typical neural network summation and doing multiply, add, and take a threshold feature of the neural network. Okay. And you will benefit from the curving as well, because that we already show you the higher order function of the accumulator. Okay. So overall, your Python program can be of different stages. You have input, doing functional programming. If you need to speed up, you can use Tensor, PyCuda, okay, to help the speed up of the function. But you in the higher level, you do use a function, calling function, calling another function. Okay, so that's a functional programming. And low level, you would want to map to higher, faster speed processor for the AI purpose. Okay. Now let's look into each of the functional programming feature in more detail. First one, let's look at Python higher order functions. So higher order functions, a function is called a higher order function if it contains the other function as a parameter or return the function as its input. For example, the function operate on the other function as are known as higher order function. Okay, and it is worth knowing that this higher order function is applicable for function and methods as well as take function as parameter or return a function as a result. Python support the concept of higher order functions. So property of higher order function. A function is an instance of the object type. So function is an object. You can store the function in a variable. You can pass the function as parameter to another function. You can return function from another function. You can store them into data structures such as hash table, list, dictionary. In Python, a function can be assigned to a variable. The assignment does not call the function. Instead, a reference to that function is created. Consider the following example. So here we have this one. We have a function called shout. And then shout will convert the text to upper. So we shout hello, you convert it to upper. That is a capital hello. Okay. So here we can assign a function shout to a reference called yell, and yell will deliver the same result. So you use a shout hello or yell hello, you get the same result. So that one is to use function as object. Pass function as argument to other functions. So functions are like object in Python. Therefore, they can be passed as argument. Okay, they can be used as argument. So here we have shout, we have whisper, and then there's a greet function. Greet function, you can pass the shout function or whisper function to it. Okay, so here greet shout. So we pass the shout to there. Okay, so basically greeting is a function call. Okay, you call that there's a fixed message. So here you greet shout that will call greet function and pass the shout to there, but the content already been there. So you print out the uppercase for this message. And greet whisper actually will convert it to lowercase. So we pass whisper and shout to the greeting function, and it presents the data in different way. And you can return function, okay, return data function. Okay, so this one actually function is a return type. So here you have a creator, okay, and you put the x as parameter and you create a aider function that being returned. Okay, so here you have this function called creator. So the creator, you will create an aider which will add 15 with a variable. So the parameter list of the aider 15 is here. The y is its parameter list. Okay, so this one is a factory. I think we showed this one before. Okay, so this one is the return of the function. And currying is converting a function that takes multiple arguments into a single argument higher order function. A function carrying any two argument function. So here, okay, here actually we have curry 2. Okay, so you pass a function. So function is a parameter being passed to here. Okay, so this is a curry 2. Okay, so curry 2. You take a function here. Okay. So here we are going to return a function g. So a function g will be created. And what is this function g? This function g actually will, by itself, it will return an h function. So function g itself will return an h function. And this h function will do what? It will call the f function with x and y. Okay, with x and y. So basically, y is the input. Y is the real input to this function. Okay, y is this input to this h function. So basically, I'm sorry, x is the value for this function. So x, actually h will be doing qualify for f x. Okay, and the h function will take a value y, you will actually process the y. So let's look at this one, okay? The h function will return a function that actually take y. So basically, you call is f function, and that take the y, okay, that take the y. Okay, that take a y parameter to here, right? That's this one actually, you call this one, okay? And your h function, this one is actually your h function. Your h function will return the result of this fxy. Okay, that's your h function. Okay, and your h function actually, your g function is actually, your g function will provide the x. Okay. And then you that will modify your f function by giving the x to there. Okay. So basically, the g function is a function generator. That function generator will generate a function called h, and h will call the function f function. Okay. And curry2 function is also a function generator that will pass the function f decorated with a, you will return with a g function. And that g function actually will create a new function that take a single input y, okay, and qualify with 2. So basically, curry2 f function, it is a function called makeAider. Okay, it can make aider. So this makeAider will take a parameter to make a aider. Okay, so the parameter is 2. So makeAider2 that will create a add2 function. And this add2 function will take a parameter of 3 and now return 2 plus 3, and you get 5. Okay, so this is two-level curving function. Two-level curving function. It create a curly 2 create a make adder function. Okay, and then this one is to create a function. Okay, curly 2 is to create a function, and first parameter will be used to create a 8-2 function. Okay, and that is the parameter to change the way the function work. Okay, and then the real parameter to the 8-2 function is this 3. Okay, so that's a curly 2. So this curly 2, you can also use this lambda expression for it. Okay, so your f lambda will create a return value. Return value is a lambda function, so itself is a function. Itself will return a function. Okay, so curly 2 will return a function. What function? This function will take a parameter x to create another function. So this lambda x is also the so-called function generator. You generate a function. Which function? You call it f, and then with parameter y. So lambda x function is actually 8-2 function. Okay, it's also 8-2 function. So this is the same as the previous one. We use this curly 2. Okay, so use case for curly. Okay, so here we can do curly, and okay, we can have 3 number, and then we apply transform to each one of them. Okay, this is somewhat like a mapping. Okay, somewhat like mapping, and here's basically the transform function is what? Is create a adder function with CT. So this one is creating the XCT function. So XCT function being applied to each individual numbers. You get 63, 64, 65. Okay. Okay, so here we can actually put that transform function. Okay, here we have a transform function. So instead of using curly, we put a lambda function to create make adder function. Okay, so this lambda x function that would actually make adder CT, that would be an adder CT function. So that will return XCT and the x function. And apply them to your 3, 4, 5. Okay, and here we have curly number 5. Okay, so your curly 2 is this one, we know. Okay, and you can use a HTML tag function to wrap up the function and with P. Okay, so P tag is this one, 18 the tag. So we can also call this one as a wrapper function. Okay, it wrap the text. You will wrap the text. Okay, you will wrap the text for it. Okay, there's a tag name. You wrap the text with the tag name. Okay. So your curly 2 function is to what? Your curly 2 function is to make a function. Okay, you make a function. So you make a function by using your HTML tag. Okay, they are making the tag. Okay, so this one P tag, this one is a make tag function. This part is make tag function. Make tag function and use P as a tag. So P tag is adding the T. This function P tag is adding the P type tag function, and your hello will be added with the P tag. Okay. Okay, here we have this one is a wrapper function, and you can use a partial. Okay, partial. Partial means you apply the function with partial parameter P. Okay. partial parameter P. So the P is used to the tag name. So it actually it's kind of like decorator. You decorate your P tag function with P, so that fill in a certain part of the parameter. So this one we call it currying, because currying by definition is converting the function that make multiple argument into a single assignment. Okay, so basically this one is we create a function, okay, P tag using the HTML tag. Okay, so HTML tag is a function. It take the tag name, so you take the T tag name, and this whole thing we create a new function called P tag, and then it take your text, and you create a P tag with the text. Okay, that's a new function you get. We call it partial, or we can also call it curry. Okay, so this is very important. Okay, it's very important to decorate your function. Okay, so decorator is similar to this curry. Okay, it is also a wrapper function. So here we have a trace one, trace. Okay, so trace function is going to print x, okay, and then call the function f of x, okay, and you return trace. So trace one function will generate a function that will trace x, okay, that will trace x, okay, and trace x you actually create the arrow, okay, you create an arrow. So right now you can trace one square, so that will trace one square, and trace one square will return a trace function. The trace function will execute a square function on the parameter. So your 3 being passed as a parameter, and your traced function will add in the 2 printing function to it. Okay, so something like that. And you will return the value R. Okay, so the value is 9, and you actually will print it as well. Okay, that's declarative function. Okay, so that is declarative function, and we can put a decorator trace one. Okay, so basically trace one will accept the function square. Okay, so square function will be called by trace one function, and you are passing the square to here. Okay, so declarative function means that you wrap up, create a new function using the trace one. So trace one is a function. So your square function is passed to trace one. Okay, create a new function. Okay, so this thing we actually can use a decorator. Okay, trace. Okay, on the definition of the square. Okay, so this one will transform the square function into square 2 function. Okay, square 2 function. Okay, that's we call it decorator. So basically, the decorator transform this function, take this one as input to the trace function, and create a new function. Okay, so that's what we call a decorator function. Okay, decorator function that we show over here. Change the flavor of the function. Okay, change the flavor of the function. Okay, so this is trace function. And attribute, okay, attribute you actually apply the attribute function to this A function. Okay, so something like that. And you can make any, can be any expression, okay, and you basically apply it to it. Okay, so you make the function with a certain attribute. Okay, chain rule is actually creating function with many chain. Okay, so let's look at this one chain. Okay, chain rule. I do not have a slice for it, but let's look at this chain function. Okay. Okay, so let's assume that here I have defined a function increase. Okay, increase. Okay, increase, and we get this one. Okay, so that's assume that this increase function will increase by a step. Okay, step data. So it actually increase by step. Okay, so here we can create a function that actually will actually make a function. So this one is okay, make increase. Increase. So this one you pass a function here. Okay, you pass a function here, and this function will that's I'm sorry. Here that's actually create a x x value. So here I'm going to basically create a g function with y value, and I'm going to create a function. So here I'm going to return return g. Okay, so g is a function I'm going to return. Okay, so this g function may take a value. Okay, take a value. Okay, so here I may put a function. Okay, so here I'm going to put a function. Okay, and here I'm going to use a value a. Okay, so I'm going to return. Okay, I'm going to return. Calling this function. Okay, function calling with actually. Okay, so this one will do increase. So we will make a function. Okay, make a function, and we take a parameter. Okay, so here that's actually I have an increase function. So here let's put this one with some step size. Okay, so I'm going to add this one. Okay, with step. Okay, so here I'm going to define another function, h function. Okay, with x. Okay, so this one I'm going to call this function. Okay, and then with actually x and step. Okay. That is a value. Okay. So this one is called make function. Okay, make function. So here we can do make function. Okay, we pass the increase function. Okay, pass the increase function. So this one will become make increase. Okay. So here actually this one actually increase by 2. Okay, so increase by 2 function will make increase. Okay, with 2 make increase function by 2. Okay, and then we will use that to call an x. Okay, call x. So here actually increase by 2. Okay, and actually let's print. Okay. Okay, let's start from 1 and actually we increase by 2. Okay. Num type is not callable. Okay, so here increase by 2, we make increase. Okay, so make function of the increase, we pass increase over there. Okay, and now we return g. Now return g. So here the make increase This one is the step. So the step, okay, so G function is made increase by 2, okay, that actually, okay, a G function. We define this one. Okay, so here right here we will return H function. Okay, I'm sorry, I missed this one. So here I have the H function. The G function will still return a H function. So this alpha H function will be assigned to increase by 2. Okay, so something like that. Let's try one more time. Okay. Okay, so get 3. Okay, you get 3. So now let's do this one. Let's do. I have initial value of x equals 0. Okay, initial value of x equals 0. So now that I have a chain function, the chain function. So this chain value will, I have a make increase. Okay, so right here I'm going to get make increase of 1. Okay, make increase of 2. Okay, make increase of 3. Okay, so 3 function created. That's actually chain functions. Okay, these are chain functions. So these chain functions I would have, okay, for each function in chain function. Okay, I'm going to do actually x equals f of x. Okay, f of x, and then at the very end, each time I'm going to print out my x value. Okay, and when I get out, I print out my x value. Okay, so let's run this one. So here add a print. Okay, to separate them. So okay, so here initially you have a 0, and add by 1 you get 1. Increase by 2 you get 2. Get 3. Increase by 3 you get 6. Okay. So that's the chain function. You result being applied to another and then apply to another. Okay, apply to another and then apply to another. These are the chain functions. Okay, these are the chain functions. Okay, something like that. So chain function, we have another way to chain it that actually is INC1 equals make increase 1. Okay, INC2 equals make increase 2. Okay. Now we have INC of 3 equals make increase of 3. So now that's assume that x equals 0 now again. Okay. And I'm going to actually separate them using a print function. Okay, now I have this x, right? And I am going to do increase 1 of my x. Okay. And this result, I'm going to do increase 2 of my, this one is my x, right? So here I can do increase 2, okay, of this value. Okay. And then I do increase 3, okay, of this value. And the whole thing assigned to x. Okay. This is another way to chain these different functions together. Okay. Really, the result is 6. Okay. So that's called so-called chain dual. Okay. The so-called chain dual. Chain dual, you can put it into a sequence of functions, okay? Or you can make the function call like this, okay? Section 7, recursion. This starts the second part that we have functions, and now we are going to apply the functions into functional programming. And a lot of time we are actually calling the function in a recursive way. So recursive function is very important. So recursive function is a function that calls itself or call some other function and then call back to itself. So it's actually calling the same function directly or indirectly. We can all call it recursive function. And recursive function often operate in increasing the smaller instance of the problem. So what this really means is actually the recursive function sometimes operate on the divide and conquer. So you may bring the problem size to a smaller case. That's divide and conquer concept. And it may involve dynamic programming. It may involve this the so-called divide and conquer. And sometimes it will also provide iteration over a collection, data collection. And this iteration may not be the iteration you think about. It may be is depth first searching or breadth first searching. It's not a linear iteration. So these are the basic concept of recursive function. And in the functional programming, we do rely on recursion a lot. So autonomy of a recursive function, you must have a base case evaluate without recursive call, and then recursive case that evaluate with a recursive call, and then conditional statements that to decide of its base case. Okay, these are the base different features that we will need. Okay, so this one, let's look at here. We have sum of the digit. Okay, sum of digit, we got a number, and we try to get the sum of each digit. So for example, we have 738. So we calculate each digit. So this digit, we use a n take modulo by 10, we get this digit. And then we take this part and continue to evaluate its sum of digit. And then that sum will plus with 8, and that will be your return value. Okay, now let's look at the 73 again. So 73, we will take the last digit, that will be 3, plus the recursive call on 7, and the sum over here plus the 3, that would give you the return value for this case. Then we go into the 7th case, and 7, we take this digit, and we'll go into the recursive call with a 0 here. And that 0 will terminate. And this termination condition, we call it base case. Or sometimes we call it termination condition. And the recursive call that breaks down the larger problem to a smaller problem, we call it recursive case. And you may also need a if statement to determine the base case. So this one is a typical recursive call function, and you will get the result with 18. So here we have a Fibonacci function, and Fibonacci function, it is using this recursive formula and base formula like this. Okay, so we may have Fibonacci function when n equals 0 or n equals 1, we return 1. Otherwise, we'll return Fibonacci of n minus 1 plus n minus 2. So it starts with n equals 0. Okay, n equals 0, you get 1. N equals 1, you get 1. N equals 2, you sum these 2 up, it becomes 2. N equals 3, you sum these 2 up, you get 3. N equals 4, you sum these 2 up, you get 5. N equals 5, you sum these 2 up, you get 8. So continue. Okay, this is the so-called Fibonacci sequence, and it actually is related to the golden ratio as well. But here we don't go into there. And here we are trying to calculate the Fibonacci of 10. So we continue. You will get Fibonacci of 6, you get 13. 7, you get 21. 8, you got 34. 9, you got 55. 10, you got 89. Okay, whatever. This, you can continue to trace that down and you will get the value. And you can write it in iterative version, okay, in iterative version. So this one, you can write it in this way. That's iterative version. I'll talk about this conversion later, okay? So here, this one, you have one version in Fibonacci function in this way, and you will get another one in this way. Let's look at these two algorithms. So right here, let's actually look at here. Let's look at the Fibonacci function. Fibo. So here, let me enter Fibonacci.Python. Okay. So here, let's import the system. Okay, the system and time. Let's import these two things. Okay, and then let's define a function called Fibo function, and then it will take n in. Okay, and if actually n equals 0 or 1, okay, this one you actually can have another way to do it is like n divided by integer division by 2 equals 0. Okay, and you return 1. This is another way you can write it. Okay, otherwise you return Fibonacci of n minus 1 plus Fibonacci of the n minus 2. Okay, so this function, let's do it. So here we do what? Let's do this one. Let's actually do 4. Okay. This one we have I, okay, in range. Okay. So here I set up n equals 40. Okay, n equals 40. So here I started from actually range of n plus 1. Okay, and this one will calculate the Fibonacci function from n equals 0. Okay, I'm sorry, I equals 0 to I equals 40. Okay, that actually is the n number. And here we will print our Fibonacci of the I value. So let's look at this case. Okay, let's save and let's run. Okay, keep going, keep going, keep going. Okay, keep going. Okay, start to slow down. Okay, start to slow down. Okay, start to slow down. As you can see, start to slow down. So the performance is one issue for this recursion. Performance is one issue if you look at this recursion. So let's look at our homework site. Okay, one moment. Okay, well, you bring it up. So it's keep going, keep going. Okay, so apparently I forget to write the number, the step. Okay, so here I should also print on my. Here I should also print on my Fibonacci of the i's value equals another integer. Okay, something like this, and I use a percentage sign and then I and Fibonacci of I. Okay, these two values. So next time I'm going to run it. Okay, run it in this way. So keep going, but it actually is slow. Okay, it actually is slow. Here, let me go to my course. Okay, and in project number 1, we do teach you how to measure the time. So let's go to the week 4 assignment, project number 1. So project number 1, we do have the measurement of the time. You import time and then get time to time, and you subtract them. Okay, you subtract them, you will get time. So here, same thing here. we will measure each time. So here we would have start equals time to time. Okay, and here we would have end equals time to time, and we will print the people of percentage D, okay, takes this amount of time, okay, and we will enter the I and end minus star. Okay, that's the time that it take. Okay, so right here it keep going, it done, or it is done. So here let's drop down to 20. I don't want to wait that long. Let's drop down to 20. Okay, so 1 to 20. So let me actually rerun this one. Okay, we know that it's too slow, but I run it once. Okay, so you keep going, keep going, keep going. Okay, keep going. Okay. The printout for Fibonacci has something wrong. Okay, so here, okay, this one I have some errors. Here it should be percentage. Okay, okay, it's done. I'm sorry. So let's try again. Okay, it takes such time. I think it's the unit may be second. Okay, the unit may be second. So here let's try it as second. Okay, and here because I don't want to screw up, so here let's use what times. Okay, times equals empty string. Okay, and here I don't do this. Okay, I actually do this later. Okay, I can't take the time, but I don't actually put it right away. I would add the time into my times in, so I can separate my time and my Fibonacci number. Okay, so here I would have my times of the i's value. Okay, so this one, let's look at it. Okay, save and run it one more time. Okay, so Fibonacci number up to 20, and the second you actually okay. So now let's add to 30. Okay, up to here still okay. It's actually 0.4 seconds. So let's try to add up to 40. So it will slow down because the last few cases will be slow. Okay, go up to 33, 34, and time slow down, 35. Because you're 35, you need to call 35, you need to call 34 and call 33, okay? So you almost double the time of the 33 case, okay? So you can think that the time almost double every time. A little bit less than the double time. Okay? But it will slow down. It will slow down. And as you can see here, we are at 38, but it's really slow now. We are almost done, okay? So have some patience. So 39 or 40 will take a longer while, okay? So 39 is done now. We pretty much have another double time from 39. If you look at the time ratio, it's not 32. Roughly, it's about 1 plus square root of 5 divided by 2 times. Okay, the golden ratio time. Okay, it's not exactly 2, 1.8 something. Okay, if you look at it. Okay, it's coming. Okay, soon, coming soon. Let's have some patience. Okay, 40 is down. So here the first few cases is good, but the last case actually take 43 seconds to finish the last case. Okay, and as you can see, the time keep rising. So that's actually punch the number. So here we do have roughly, okay, roughly we do have here we have 43.76. Okay, so 43.76 divided by 26.18. We've got a ratio of 1.67. Okay, so roughly that's the golden ratio value as well. So now, okay, we are this one is too slow. Okay, and we do not need a 6, so we can delete that. Okay, so here let me save, and I'm going to copy this one to another one. Okay, copy this one to another one that actually is the Fibonacci 2. Okay, that py. Okay, Fibonacci 2.py. Okay, so this time I'm going to write the so-called iterative version. Okay, so this is Fibonacci function. I'm going to redo it. Okay, I'm going to read it. So you got a n. Okay, you got an n right here. Okay, you got an n right here, and we are going to calculate the Fibonacci function. So previous one we use a recursion to do it, right? And here we don't use a recursion, and we take the number of n. Okay, so here if actually n, okay, here if n divided by 2 equals 1, then we will still, I'm sorry, equals 0, we will still return 1. Okay, that actually is the first two terms. Okay, after that we will say we would have the f value. Okay, we will have the f value. We will have fn minus 1. Okay, so n minus 1, let's assume is this value. Let's set it to be 1. Fn, okay, actually 2. That one will be actually 1 as well. Okay, so here while we will do while I, okay, we will need to have the current index I. Okay, so I that's set to be actually 2. Okay, set to be 2, and then while I less than equals the n. Okay, so when you get out, I will be when you get out I will be greater than n. Okay, so in here we do f. Okay, so here we will have f number. Okay, so f number is set to 0 for now. So f will be equals fn minus 1 plus fn. Okay, 2. Okay, this is a new f value. Okay, this is the new f value. So now your f of n equals fn minus 1 plus fn minus 2. So initially you have f2 equals f1 plus f0. Okay, so this is n minus 2. This is n minus 1. This is n. Okay, and the next one you have f3 equals f2 plus f1. Okay, so here you actually push your f1 to here, f2 to here. Okay, so that's the recursive relationship we can find. So your f of the n minus 2 will be your f of the n minus 1. Okay, and your f n minus 1 will be your f. Okay, that's the recursion. And we keep doing this until we are done. Okay, until we are done. Then right here, at the very end, you will return this f value. That's what you want to have. Okay, that's what you want to have. And at that time, I will be stuck at I equals n. That's what you have n. Okay, so when I equals 2, if n equals 2, n equal 2, I equals 2, you get in. Okay, you calculate it once, you get out, you get f of 2. Okay, and if you have I n equals 3, then you calculate f2, you have one more iteration, and then you calculate f3, and then you stop. So that one should be okay. So let's look at this one, the non-recursive version, okay, using the same timing measurement setup, okay. Something wrong, okay, something wrong. something wrong. Okay, something wrong. So I go into some trouble. Okay, I go into some trouble. Let me actually save all first. Okay, I forget one thing. Okay, sorry for that. Let me redo it. Okay, let me redo it. I forget one thing because I forget to update my I. Okay, sorry for that. I forget to update my I. That's a stupid mistake, but it's okay. That's not too hard. So let's use a Window R. Okay. My my code is okay, but I forget to update my I. Sorry for that. After I run, I realize that. Okay. So here let's call code that. Okay. Bring up my Visual Studio Code. So most of the recursive function, you can convert it to your iterative function, okay? So here for each I, okay, Fibonacci 2 here for each I. Here, I also need to update my I, update by 1, okay? Otherwise, you are not really updating your value, okay? You are not really updating your value. Your I need to be advanced as well. So here, that's actually wrong again. Let me see, actually, let's see, okay? Okay, still trying to discover the interpreter. Okay, let's wait a little bit. Okay, see, almost no time, but the data is the same. Data is the same, but almost no time, even 40. Okay, so let's keep trying bigger numbers. So let's try Fibonacci of 300. Okay, set all and actually run. So even Fibonacci of 300 does not actually take too much time for this solution. Okay, and let's check the internet for first. Okay, 300 Fibonacci. Okay, first 300 Fibonacci number. Okay, so here. Okay, it uses F0 equals 0. Okay, so it's 1 off. Okay, so my F2 equals my F1. His F2 equals my F1. So here is F300 should be my F 299. Okay, so here this one is the value. Okay, here. Okay, it's a value here. Let's actually look at my solution. Okay, there's a 2222 something. Okay. So the 2222 something is my 299, okay? So actually the same, okay? Okay, so that is Fibonacci number, okay? That's actually is a Fibonacci number, okay? Right here, why I bring up this one up for recursion is number one, recursion, if you have a branch case of higher than 1 degree of order, you are in trouble because your function will explore exponentially. So you have a function f of n, you actually try to call f of n minus 1 and f of n minus 2. Very likely your time will be order of 2 to the power n, okay? So if you find this one out, it is not suitable for recursion, okay? I try to not to have the degree of call more than 2, okay? So look into my the so-called iterative version. The iterative version, we pass a n over here, right? We pass a n over here. So this n is actually 30, okay? So you start from 2 and then 3 and then 4 and then 5, okay? And you have f2 equals f1 plus f0. This is constant time, okay? Constant time. And you ship the data, and you get f3 equals f2 plus f1. So it's constant time. So constant time. And you run it for 30 times, actually 28 times, but time C is actually what? It still be a constant time, okay? Even if this one is an N, so it's actually an order N algorithm. Okay. Each iteration only is constant time, so it's way much faster. So why people like to discuss the Fibonacci function in recursion? Just because it is a good educational material. In terms of performance, it makes no sense. It made no sense. Okay, that's what I'm trying to claim. Recursive function can write a function much easier, but you must make sure that your recursive function is efficient. And the way to manage it is try not to have this one. You have multiple recursive call within the function. It will explode into the exponential time. Okay, in that case, you would rather to have an iterative function to do it. Okay. So you can verify the Fibonacci algorithm, okay, and check the data, okay, to verify whether it's correct, okay. So now that is Fibonacci function, but sometimes we may want to write some recursive function, and you would like to write the so-called helper function first, and make sure it passes through enough argument to the subcases and the expected result. Okay, so let's look at one example. Here we have this one is a binary search function. Okay, so regularly you actually get the low and high, right? And when it has a crossover, you will stop. Okay, that means that you don't have the data. So binary search, you have some data over here. Okay, so let's assume that we have 7 numbers. Okay. And you have 1, 3, 5, 7, okay, and then you have 9, 11, and 13, okay. So let's assume that we are trying to search for the data 2, okay. We pass a key as 2, and the first one we go into here to check this value, okay, is less than, so we go this way, okay. Second one we check this value, okay, by the calculation of midpoint, we check this value, still smaller than, so we check this value. And it's greater. So right here, we will see this value is over here, but we cannot find it. So there will be a crossover, and then you got -1. Okay, you got a -1. That means that you don't find it. Okay, that means that you don't find it. And the index, okay, the index is actually like this. Okay, the index initially your low actually is pointing to here. Your high is actually pointing to here, okay. You divide by 2, you get the middle point. That's over here. That's the first one. Second one, because it's smaller than the middle point, you move your high from here to here. You find your middle point to be here, okay. And then it's actually smaller again. Then you move your high to be here, okay. And your low will also be here. So actually your midpoint will also be here. And it is now greater than you really move your low to be here. So your low now bigger than high, then you will have a crossover condition, and then you don't find it. Okay, so this was actually binary search iterative version. So recursive version is like this. Okay, recursive version is like this. We can have a recursive version, okay? So this one, you actually start to write the helper function first, okay? So you get an array, you have the key value you want to check, and you have low and high index. So when you have low and high, that's actually crossover, that you return -1. That means that you don't find it. Otherwise, you use a low and high to calculate your mid value and then determine. If the A's mid value equals key, you return mid. That means you found it. Otherwise, you will check if the mid value greater than key. That means that your key is on the left-hand side. So your high value will move to mid -1. Okay, and recursively calling this function. Okay. Otherwise, if your key is actually greater than your mid value, then your low value need to move to the mid value +1, okay, and recursively call this one. So this is the way you write your binary search, okay, and basically you write your helper function first, and then write your interface to the user, okay, the interface function to the traditional a recursive function. So this is the way you write a recursive function. Okay. Next topic is the mutual recursion. Okay, mutual recursion is a function that two functions that call each other. Okay, so here we have a loom algorithm to verify that credit card number is valid. Okay, to verify credit card number is valid, we use a loom algorithm. So this loom algorithm from the rightmost digit, which is a check digit, okay, move to the left, delete the value of every second digit, okay, every second digit, and then if the product of this doubling operation is greater than 9, then the sum of the digit of the product, okay, sum the digit of the product. So here, take the sum of all digits. You start with the check digit that is 3, okay, and you make that, okay, double its value of every second digit, okay, every second digit. So here, every second digit means you move left, you try this second digit, okay, so double that, okay, so double that you get 8, and it's not greater than 9, so you don't need to change it, okay. So now this one, next one, you get 7, it automatically drop the 7. You drop the 7 from here, okay, so drop here, this one here, and then you double to get this one. So you are going to get 14 in that case. I'm sorry. You actually will, I'm sorry, you double the 8, okay, double the 8. Double 8, you get 16, so you need to take the sum of it, okay. So this one you need to call, the loom algorithm, you need to call the sum of digit, okay. You need to call the sum of digit, and you need to take recursion one by one until you actually finish it, okay. And you drop 3, and then you double it, okay. So that's the value you got, 2, 3, 7, 7, 8, 7. That's the first pass, okay, you get all of these. Then the loom sum of a valid credit card is multiple of 10 because you sum this whole thing up. You have 2, 3, 7, 7, 8, 3. You got 10, 20, 30. You got 30. Okay, that's a multiple of 10. So here is sum of digit with less than 10, you will return n, okay, you will return n by itself is less than 10. If it actually greater than 10, okay, greater than 10. So this one is sum of digit, okay. So sum of digit, you get a n's number, okay. If n less than 10, you return the n value, okay. And if not, okay, if not, then you take the last digit, okay, and then you get the O by last, okay, O by last, and you try to get the last one plus the O by last value. Continue to get sum of digit, okay, sum of digit. So you continue to do that, okay. So this one is a sum of digit. It will add the sum of a number, okay. And this one we can rewrite it in different way, okay. This is one way you can do it, okay. One way you can do it. That's the sum digit, and your loom double function, okay. Your loom double function. You have loom sum and you have loom double function. So we can rewrite the whole thing as such, okay? So here we do have the loom sum. Loom sum, we will actually sum up all the loom, n number, okay? If n equals 0, you have nothing, okay? Then you actually will actually do this, okay? And you calculate loom double, okay? So loom sum double, this one is loom sum double. You actually every time you got some digit, okay, here you actually have loom sum double. You take the last digit, okay, the last digit, and then you take the O by last digit, okay, and then you have the loom digit is actually the last digit times 2, okay, last digit times 2, and then if less than 10, you actually do use what? Use a lump digit, okay, otherwise do lump digit plus loom sum. So you're rotating loom sum and loom double. You're rotating loom sum and loom double. What are these? So basically what it is you originally have some data, okay? let's actually go back to the example. So we have 138743, okay? We have 138743, okay, we have this, okay? So here, apparently the last one, we are going to do, this one, we are going to do room sum. So room sum, we put the whole thing in, we try to do room sum. We try to do room sum, we actually process this value, and that's the last value here. Then the rest of them, we actually, this portion, we pass to room double, because the last digit we will use the double rule to calculate it. Okay, and you will do sum of the digit for this the data, okay, when you multiply by 2, okay, and then you finish that one, you pass the function, pass the value to the room sum again. So basically here call the room sum, this one call room sum double, this one call room sum, this one call room sum double, this one call room sum, this one call room sum double, and you will be able to get the right room sum value, okay, and check if it's multiple of 30. So this two we find out is we have the so-called coroutine. Coroutine happens when A function calling B function, and inside B function somewhere also call A function, okay? And both of them have a termination condition. Both of them actually have its own termination condition, okay? And we call this kind of program called coroutine. And these two coroutine do call the sum of digit, okay? Do call the sum of digit. So that's the recursion, okay? Mutual recursion. Now we finished the discussion with the recursion. The next topic we will talk about is the data collection and how to apply the function onto the data collection. So data collection, we may have tree, we may have list, we may have graph, and the function being applied onto them. So function would apply onto them. Maybe recursive, maybe non-recursive, but function will be applied on these data structures. And that's the purpose of this chapter, that is to apply the functional programming to the data. So here is a simple tree. A tree usually have a root node. The root node is the topmost node. This one is a root node, okay? And a tree won't have cycle. It should not create a cycle. So tree don't have cycle, and it has a root, and each one of the branch, okay, here we can call it a node, okay? So here we have several node, each one of the node. Each node may have its value and its branch, maybe left branch or right branch. And the degree of branch may be 0, maybe 1, maybe 2, maybe more, okay? So it's not limited to only 2, okay? But if only 2 branch on each node for each subtree, then we call it binary tree, okay? Then we call it binary tree. But here, assuming that the degree of the branch may not be exactly equals 2, okay? So each node will have child. We can call it child, left child, and right child, or many other child, okay? And it has different branches under it. Okay? And for a node that don't have child, we call it a deep node. We call it a root node, okay? And sometimes we can call the node with child a branch node. Okay, sometimes we can call it that way as well. Okay. And the degree of the label that you have. So right here is 1, 2, 3, 4. So that is the depth of the tree. How many labels you have, that's called the depth of the tree. Okay. And you may have a total number of 1, 2, 3, 4, 5, 6, 7, 8, 9 nodes. That can be the size of the tree. Okay. So these are basic terminology for a tree. So a tree can have recursive description. A tree may have a root label and a list of branches. Each branch is a tree by itself. So you can call it a subtree, okay? And a tree with 0 branches is called a leaf, okay? And a tree starts with root. Relative description, each location in a tree is called a node. Each node has a label, or sometimes we can call it a value. And one can be the parent or child of another. The top node is called root node. So data description, you can have a tree and with a label, the current label and its branches, okay? Branches. So branches usually can be a list, can be a tuple, can be a data collection. And label, when you call label or the tree, you will return the label or the value, okay? And branches, you will get the branches of the tree. And if leaf, you check if the node is a leaf node or not. That depends on how many branches he has under it, okay? So here, these are the very simple description of tree, and you put a label and branches, okay? You can put the branches into it, and that create a tree, okay? That create a tree. That actually you have the label, you put the label plus this, you kind of creating a data structure like this. You have a list, okay? So that is the label. And at the label, you actually have a branches list. So that this one we create use a list as tree, okay? This one is list as tree. So use this as tree in this implementation. Okay, and then you can have tree of the label, you get the 0. Get the 0 means in your data structure, you do have the label over here. So this one is your tree 0. Okay, you get a tree, you get tree 0, that's your label. Okay. And tree 1 and after, that actually is your branches. It's your branches. Okay. And this one is plus, so it actually is concatenation. So you may have multiple nodes, so actually may have node 1, node 2, node 3, okay, several nodes, okay. And each node may be another tree, okay. Each node may be another tree. So that's a tree, and you can have each, if leaf, actually you're trying to check the length of the branches, okay, the length of the branches, okay, the length of the branches. So referential branches, the branches may be empty, okay, maybe empty. So here, this one, tree of 1, that is a deep node, okay. So something like that. Okay, so this one, you bring the tree using such a notation, okay, such a notation. Okay, tree process, the tree is a recursive data structure. Each tree has a label and have a few branches, okay. And recursive structure means recursive algorithm, okay. So you can count the leaves and you get a tree, try to count the leaf. If a tree is a leaf, you return 1, okay, you return 1. Then you calculate the leaf under it, sum up all the branches, okay, sum up all the leaves under it for each branches, and then plus your current node, okay, that's actually it will be your total number of the leaves under you, okay? And you can count the leaf sum, okay? So you actually can visit all of the leaf nodes and then get the, if leaf, you return 1, okay? If leaf, you return 1, okay? And you can count the leaves, okay, sum based on each of the branches. So this one is using the count the leaf sum recursive function, okay, recursive function for it, okay, recursive function for it. So compared to this one count leaf you actually using for loop, and this one you actually use a what? Use a comprehension list format, and you calculate the sum based on the sum in the list. Okay, this way and this way get the same result. Okay, you can compare the differences. Okay, so copy from one tree to the other, this is called tree duplication. It is also a recursive call. So basically, if you leave node, you tree label the current tree label. Okay. Otherwise, you create a tree with a label and the branches of each one of the branches, and you actually create a tree in there. Okay. So that is a copy of the tree. And print of the tree, you print tree. Okay. Indentation equals 0. Okay, you adjust the indentation level. Okay, so your current node, you actually use the indentation level you have, and then you print out a few spaces based on current indentation level, and you print your label. So you have a node. So that's assume that you have 20. Okay, and under it you have 7 and 12. Okay. So you print out 20, that's no indentation. Then you keep 3 later and you print 7. Okay. And after 7, you may have a few nodes under 7, then you print it here. If not, you will go back to 2, print your 12. Okay, that's also leaves 3 nodes. So each level you actually can have an indentation of +3, and that can differentiate different tree level. So sum list, okay, you can. This one is grouping of arguments. So basically, you can pass in A, B, C, D, several values. Okay, so that's the argument. So each one of them, you actually try to sum these arguments. Okay, sum these arguments. So this is a sum list of these. Actually, you will sum. Okay, you will sum the list of this argument. Okay, so basically, you sum this of this one 1. That's actually the sum of this guy. Okay, sum of this guy. And then you will do, you actually have a list. You get a list. So you get this list, okay? And this sum is an empty list. So 1 being absorbed, right? Next one, you get is a 2, 3, that's a list. And you actually connect them together. So you do connect 2 and 3 into there. And then you get a 4, and then you put the 4 into there. So this one is a fraction of the list, flattening the list. Okay, sum list actually is a flattening of the list. Originally, you made tree structure, but you can flatten them. Okay, sum list. Okay, so that here we can check if some data is deep. Okay, you will try to get the deep of it. If you the deep node, you will actually retain itself. Okay, and otherwise you will actually try to find the deep of all the branches, and then you actually sum the current label with all of the deep labels in the different sublists. So it actually will group together all of the deep labels together. Okay, only the deep. So basically, right here, your deep only have this one, this one, this one, this one. Because when you check a deep, you will return the data. Okay, if it is not a deep, it won't be returned. It won't be returned. Okay, so you go down to each level to collect the deep node of the lower level, and then you collect them. So this one we can collect all of the deep node of a tree. So counting paths. Now this one is counting number of paths that T can traverse to. So basically, counting paths, if you are the deep node, you actually have 1 path. Okay. Otherwise, you will sum up all of the passes of your branches. Okay. And then that's actually, you have a total. Total is a value. Okay. Total is a value. Total is a value, and that value will subtract the label. Okay, subtract the label of the tree. Okay, the label of the tree. So right here we actually count paths of the 3. Okay, so count paths of the 3. We go to this one. Okay. So here we have this one. It is trying to actually, so total is the number that you want to match, okay? So here we would like to see how many paths that has 3, okay? So you actually will have, say, here we have 3. Okay, 3 actually is 3. Okay, and then you have -1 is 1 node, 1 is 1 node. So we have 3, -1, 1, and 1 had 2 and 3. And here 2, you have 1. Okay, and you have 1. Let me see. Okay, let me see. Let's actually try one more time. Okay, so here your top level you have a 3. Okay, and under it you have, this is 1 tree, so that's a -1 over here. You have another one that's actually 1. Okay, you have another one that actually is a 1 over here. Okay, and this one you have, let's see, this one you have 1 over here. Okay, this one is this 1, and 1 you have 2, and 1 and 3. So 1 and 3 is another. So there is a 2. Okay, and that 2 has actually 1 and 3. Okay, there's another 1, and there's a 1 under it. Okay. So we're trying to find a path of 3. You go here, okay. And 4. So this one is actually you have a TS. TS is your root node. Okay, TS is your root node. And then you try to find out how many paths that will sum up to 3. Okay, sum up to 3. So you compass with a certain B. Okay, B actually is a tree. So you with the tree, and you must minus your own node. Okay, minus your own node. So here you actually sum up each branches and actually take out all of the value. Okay, so if the label equals the total, that means you go down and the remaining label is the same. So you will get it. Okay, so you have the fun. Okay, you will have the fun. So it will depends on how many nodes you have. So here we have this one. Let's look at this one. This one is 3 of 1 and 3 of 1. So that one is 1, 1 here. Okay, that's 1 node. Okay, here this one we have a 3 of 2 and 1. So this one is 2 and 1. That actually is 1 node. Okay, that's actually is 1 node. And then that's the first node. And the second node, you have a 3 of 3. So this one is a structure over here. Okay, there's a 3 of 3 over here. So that actually, okay, these 2 actually are equivalent. So I'm sorry. These 2 actually should be 2 and 3 are same level. So 2 and 3 are same level. 2 and 3 are same level. Here you have a 1 under it. Okay. And then on top of it, this one is a 3 of 1. There's a 1 over here. Okay. And the 3 of 1 and the -1. Okay. And the -1, these 2 are under 3. Okay. So there's a -1. So -1 is a root node. Okay. -1 is a single tree node. -1 is a single tree node. So here you do have 1 as a branch. Under this branch, you have 2 and 3. So here you have another one is 1, 1. So this is your 3 paths is like this. Okay, 3 paths like this. So here to match a path of 3, okay, let's see. To match a path of 3. So here we certainly can find here, this is 3, 4, 5. So 5, you can see this one is a 5. Okay. 6 actually is, you can see a 6 over here. Okay. 7, you can see a 7 over here. 7, this one is 6, 5, this one is 6. Okay. And then you try to look at 3. 3 is this node. Okay, 3 this node. And 4, you have 3 and 1. That's 4. Okay, 3 and 1, you have 4. Okay. And this sum actually Sum actually is taking the sum of all of the labels, all of the compass, okay, all of the label of the compass, okay. That's the sum of all the label of the compass. Okay, so this one is to count each value's possible path. Okay, each value's possible path. So 3 level abstraction for a tree, you do have this one, 1, 2, 3, A, B, C. Okay, and that is a list. Okay, and the tree, you have branch, leaf, row, and label. Okay, you can copy tree, print tree, leaf tree, and count path. Okay, type of tree, you have data tree. Data tree is you organize the data in a tree. That's called data tree. So usually you may have binary tree, you may have data tree, and that represents it. You can have a component tree. Component tree means your top level graph is like this, but you do have a component of, let me see, okay, you have a component actually inside here, okay, so that's actually clear it. You have this one, this this parent node, okay. So actually you have this 2 here, okay. Let's see. You have component tree. So component tree means that you have some component of different cases that can derive from your parent node, okay. So here you may have 4 node and 2 green, 4 node, 2 green, maybe this one, you can have this, okay. Something like that, okay. This one is the pattern that you can generate from the parent tree. You can have 2 and 4 separated. Here we have 3 and 4 separated, okay. So this one you can have 2 green and 4 of these, you separate this one, okay. And then you have, okay, here I think it misses somewhere, okay. But this one is the component tree, okay. You group part of the components and make it a tree. And you may have an expression tree, okay. Your algebraic expression, you can make it as a tree, okay. And you may have this one called classification tree, okay. Classification tree or decision tree. You may decide the shape, maybe triangle or square, okay, and you have straight or rotated of different shape, okay. This is decision tree. So decision tree is based on your decision branches you go down, okay. Expression tree is you actually group your expression into the tree structure, okay. Component tree, you actually topologically divide some portion into a tree, okay. And you may have recursion tree. Recursion tree such as a Fibonacci tree is a recursion tree, but recursion tree sometimes did not build the tree itself. It actually just a function code. We call it recursion tree. And you may have gain evaluation tree, say this tic-tac-toe. You have different start point, center point, or some side point or some corner point, and you have developing the strategy called gain evaluation tree. And you have parsing tree. Parsing tree means that you parse your tokens based on your grammar. And this one will be heavily used when we go down to our future chapters for the syntax analysis. This is the parsing tree. And you may have binary search tree. So left side smaller, right side bigger. That's called binary tree, okay. And you may have directory system tree. You have a root node and several subfolders, okay. Several subfolders. So this portion for tree, basically we introduce some representation for the tree and talking about how to build the tree functions and counting the tree label and tree paths, okay. That's a basic operation for tree. And then we talk about the possible representation of the trees and what kind of data, expression, or component can be grouped into tree. And as for how to use them is yet another story. We will use our later chapter to discuss it. So here we finish the tree, and the next one we are going to move on to stack and pushdown automata about language translation. Okay, so we'll combine the stack and tree and data representation and the evaluation for it. Okay. Section 11, Introduction to Pushdown Automata. Pushdown Automata. Why we are discussing it here? We have some tokens. We have A plus X plus Y plus 2, okay? And this whole thing can be converted to a evaluation tree such as X plus Y and then plus 2, or you can convert it to be S plus Y plus 2. Depends on how you pass it. Depends on how you pass it. So our original token string is like this, but the target evaluation tree is like this. So now we want to change the order of the execution in order to build this tree. So we look at the X, we push it into the step. And when we get a plus sign, so we put it as a plus sign, and we finish another token that's actually Y. So then we actually see that Y coming in, okay, or it finished. Then we actually pop out the Y, okay, pop out the Y, and then we actually create such a subtree. We create such a subtree, and then we actually push it back to the step. So that's when this one is expression 1. So then we push in the expression 1 into it. And then we push in the plus sign, and then we see the 2, and we pop out to create expression 2. Okay, so that's the process of translating from the tokens to build a syntax tree. But because there are several formats, so it can be prefix, infix, or different format. So Pushdown Automata is an automata that with a stack. So it is a finite state machine with a stack. So this in combine can describe any of the context-free grammar. Context-free grammar. Only finite state machine you can only use for regular expression. So Pushdown Automata is a way to implement context-free grammar in a similar way that we design deterministic finite state machine for regular grammar. A DFA can remember a finite amount of information, but PDA can remember an infinite amount of information because you can store it. Okay, you can actually store it. So a PDA may or may not read the input symbol but you have to read the top of the stack in every transition. Okay, you will have to read the top of the transition of the stack in every transition. So this is the diagram of using the Pushdown Automata. And you have a state variable that actually keep picking on the input and also the top of the stack. So Pushdown Automata has 3 components: an input tab, a control unit, a stack with infinite size. Okay, the stack head scan the top symbol of the stack, and the stack had 2 operations: push or pop. Okay, push or pop. So formal description of a Pushdown Automata, you can use 7 tuple. That is the number of the states, that's Q. The sigma, the input symbols, alphabet. The S, the stack symbols. The delta, that's the transition function from the input with the input symbols and the state and the stack symbols, and then output to the so-called new state and the output string. So this is the so-called transition function, okay, delta. And then there's an initial condition, that's actually initial state Q0. And there is an initial stack top symbol that's called I. And there is a set of final states, okay, final states. So it's more complicated than the so-called the finite state machine. So stack is called a pushdown stack. Okay, so it is an ordered collection of items where the addition of new items are removed of existing items always take place on the same end. So stack actually you push the data in or pop the data out from the same location. You don't actually need the data from this side. Okay. So usually we call this side as its top. Okay. And this one we call it base. So it is a one-dimensional data structure, but it has only one direction to push or pop. So stack is a linear structure in which items may be added or removed only at one end. Okay, so this push and pop. Okay, push and pop. With the stack, the most important operation is the reverse of the direction. So we can have push in 1, 2, 3. So 1 come in, then 2 come in, and then 3 come in. Then we actually pop out 3 and then 2 and 1. So first in, last out. That's the principle of the stack, and it will revert the whole order of the sequence. Okay, but that's not the only application for it. So here we have original order 8.4. Q, stay, dog, true, I'm sorry, 8.4, true, dog, and 4. And we push it into there, 4 and dog and true and 8.4. And we pop them now. 8.4 will be pop out first, and then true, and then dog, and then 4. That's the reverse order. So primary operation defined on stack will be push, pop, and pick. A push is putting the data on top of the list. A pop is the pop the data from the top of the list. A pick is the read the value of the top element. So these are 3 basic operations. And then we have the stack that will be a constructor to build a stack. And then we have push, item in, pop, and pick functions. And we also may add the isEmpty function and size function. So here we have a stack, and we check if it is empty, it will return true. So we push 4 in, the stack becomes 4. We push dog in, it becomes 4 and dog. We pick it, we will get dog. We push true in, you will get 4 dog true. We check the size, now it's 3. We check if MP is 4. We push 8.4 in, that would be 4 dog true 8.4. We pop 8.4 out, we pop true out, we pop 2 out. I'm sorry, we actually check the size of the list, it becomes 2. Okay, so that's those are operations for stack. And we can implement stack using list, okay, because Python list is the so-called double-ended queue. So you can use it to mimic the queue, mimic the stack, mimic the so-called double-ended queue or queue. Okay, you can use it for anything. And the stack data structure can be implemented by using array or linked list. So primitive collection. Python, as in any object-oriented programming language, the implementation choice for abstract data type such as stack is the creation of a new class. Sorry. The stack operations are implemented as methods. Further, to implement stack, which is a collection of elements, it makes sense to utilize the power and simplicity of primitive collections. So we may use list, that would be simpler. Okay, so we will use this, and we had append. Append is to append to the end. Pop is pop from the end. Okay, so these 2 is the basis for push and pop. Okay, so here we have a demo program called stack.py. So here we have stack, we have a constructor. When we construct a new constructor, new stack, it will create an empty list. And it's empty, will check if the items is empty. Push will append the element to it. Pop will pop out the element from the list. And then pick will be returning the top data. Okay, top data. And it will not pop out. It will not pop out here. Okay. And then we will actually check the size of the frame. So right here, this program called stack.py, it also goes through the operation we described before. Okay. So you can check the simple code. Okay, simple code. So here we have stack number 2, This one, we change the append to insert 0 and pop to pop 0, okay? And pick is actually picking at the 0. So this one, we are using the 0n, okay, 0n to do push and pop, okay? We don't use the tail side, okay? We use the head side to do push and pop. This is also okay. So the ability to change the physical implementation of abstract data type while maintaining the logical characteristic is an example of abstraction at work, okay? And here the pop function is order of 1 because you directly check the end of the list, okay? So it's an order constant time operation. And insert 0 or pop 0 is order of n. So we really like to use the pop on the end, okay, on the step 1 implementation instead of step 2 implementation. Step 2 implementation is slower because the order of n operation. So here we have this call frame, okay, for push and pop for this Python program, okay. You can try to use the so-called Python runner to check it. Okay, parentheses. So now we have a single balanced parenthesis we would like to try, okay, we'd like to try. And here there's a function called square, okay, we can define a function called square, okay, something like that. Okay, there's a function arithmetic. So here number 1 is the balance of the parentheses. The balance of parentheses is like when you open the left side parenthesis, you must have a right side parenthesis. But your right side cannot have more closing parenthesis than the left side parenthesis. Okay, so you must actually check whether it's balanced. Okay. Okay, so here is there's a problem of balance of the parentheses. Okay, so we actually need to have every parenthesis be matched by a right hand side parenthesis. Okay, so there's a parenthesis checker. Okay, so here we can actually use the parenthesis checker. We actually get a certain string. We create a new stack. Okay, and set the balance to be true. And every time we scan through a string, so the string actually being assigned to actually get a symbol from the location, okay? And then if it's left side and we push it, okay? Right side, we actually, if it's left side, we actually push it, okay? Else, if actually we do, this one we actually do push, okay? If it's a left side. If it is not the left side parenthesis, then we will check if the string is actually empty or not. If the string empty, we reach the end of the string. Okay, we actually I'm sorry, we check the stack if it's empty or not. Okay, and if we actually the stack is already empty and we finish the whole not finish the string yet. Okay, then the balance is false. Okay. Otherwise, we will pop data out, okay, pop that out for the right side. So here, this one else means that you directly pop out with right side parenthesis, okay. So if your stack is already empty, then you cannot pop out. That means you may have more right side open parenthesis than the close parenthesis than the open parenthesis, okay, in this case, okay. So left side, we call it open parenthesis. Right side, we call it closed parenthesis. So we see a left side, we will push the symbol in. We see a right side, we will pop it out, pop the left side out, okay? So, but if we actually do see, we push in 2, but we actually pop out 3, the third one actually, when it try to pop out, the stack is actually empty. So you get something wrong, okay? So that's a penalty check, okay? Okay, parenthesis check, okay. So we can also look at the balance symbol, okay. So here we are trying to balance the curly brace, the parentheses, and also the so-called brackets. Okay, there are 3 labels, so we can balance that. Okay, so each one of the label you can balance it. Okay, we can balance it. This is a parenthesis check number 2. So here actually you still read in the same symbol. Okay, symbol string. Then we create a stack. Okay, balance to be true. So every time if there's a new symbol, we read a new symbol. So if the symbol is actually in here, we push the symbol in. Okay, if the stack is empty, then we actually run. Okay, and we will pop out a symbol. Okay, if the pop out symbol and the top, okay, if we pop out symbol and then that actually we assign to top. Okay, and the symbol that we actually read in doesn't match. So match means that your left side need to be matching the right side. Okay, opener and closer you need to match. So if you try to pop out this one with this, that actually will be error. So here this one show you how you match them. Okay, using the matching function over here. Okay, algebraic expression. Okay, so algebraic expression can be defined as this. And the algebraic expression is a combination of operand and operator that represent certain values. So algebraic expression basically is A plus B, okay, times C plus D, and with parentheses with multiplication. Okay, that's called algebraic expression. Okay. So right-hand side B plus C is algebraic expression. Okay, there is assignment equals. Okay, so an operator is a symbol who tells the computer to perform certain mathematical or logic operations. Operands are the value, okay, that operator performs tasks on. Okay, so there are 3 ways to represent the algebraic expression. That is prefix, infix, and postfix. Prefix is an operator put in front. So A plus B, if you put into the prefix, it will be plus AB. Okay, infix is a normal way we write it. Postfix is A, B, and plus. Okay, so we have 3 ways to represent a same algebraic expression. Okay, and we can use stack to convert one expression to the other. So here we have A plus B, that's called infix. Okay, prefix is on the left-hand side. Postfix, the operator is on the right-hand side. Okay, and here we have different description. We can use infix and then postfix. Okay, so basically these are the description. Okay, precedence level. Okay, each operator has precedence level. So large operator of higher precedence level are used before the operator of lower precedence level. Okay. The only thing that can change the order of precedence level is the parentheses. Okay, so parentheses go first. Okay, so parentheses go first. So fully parenthesize the expression. One way to write an expression that guarantees there will be no confusion with respect to the order of operation is to create a fully parenthesized expression. This type of expression use 1 pair of parentheses for each operator. Okay, so you will have a fully parenthesized operation. So you can convert from this one to this. This is called fully parenthesized expression. Okay, and once you put it into fully parenthesized expression, then there's no argument. Okay, there's no argument. So postfix translation. Okay, postfix translation. So here we scan the symbol 1 by 1 from left to the right, given the infix expression, and then repeat step 2 to 5. If the second symbol is operand, then please directly in the postfix expression. Okay. If the scan symbol is left parenthesis, then push it to the stack. Okay. If the scan operator is an operator, okay, then actually you will repeatedly pop the stack, pop from stack, and add the postfix expression to the operand. Okay. If the symbol is right parenthesis, then we repeat pop from the stack and add the postfix expression each operand, okay, on top of the stack till we match the left parentheses. Okay, these are the algorithm. So here, let's look at example. We have A plus B times C minus D. Okay, so what we would do is first we will see a parenthesis. Okay, we'll push in, and then we see an A. Okay, A actually is an operand, so we do nothing. Okay, this one we push in the plus sign. Okay, and we see a B. Okay, we do nothing. Okay, it's another operand. So second operand we record it, and then we see a parenthesis. So we will pop out. We pop the plus sign and pop out the parenthesis. Okay, and then that finish this portion. So basically we have A plus B already, depending on what data we want to have. So right now we do have the first operand, second operand, and the related operation we have. And then you can point it this way or you can point it this way, depending on your need for the phone translation. So now we actually will push in the multiplier into there. And then we actually will push a left side parenthesis, and we'll push in a minus sign, and then push in, we'll pop out minus sign and the parenthesis. So that one will get the second operand. So second operand, so first operand right now is A, B plus, and second is C, D minus, and then these two will be time. Okay, so this one is the first parenthesis, this one is second parenthesis. Okay, and third level is here. This one, and time. Okay. So that actually is converting the infix to postscript. Okay. So we create a stack. Okay, we create a stack. Now represent variable we have multiply as 3 divided 3 plus 2 minus 1 and left side parenthesis 1. Okay. Okay, so this one will convert the function from infix to postscript. Okay, given an expression, we are going to use underline convert to convert it. Okay, and the expression will be split for the tokens. Okay, so we convert it for the tokens, and the tokens actually will be fit into it, and we have postscript list, and we have a operand state. Okay, so from the token we actually get it. Okay, so token is identifier. Then we directly take it to the postscript. Okay, so the data say right now if we read an A, we put the A into the postscript. Okay, we see the so-called parenthesis, then we'll push in the token. So right here, let's assume that we have this one A plus B, okay, times C minus D. So the first one we see is the parenthesis. So we'll push it into the stack, okay. Second one we will see is token. So token A will be right out to the postscript division. Then we'll push in plus sign. Okay, we'll push in the operand that is plus sign, okay. So that one is else, must be operator, okay. So operator is not stack, okay, not stack is not empty, okay. So we will compare the precedence, okay. Compare the precedence, okay. The temp is the top level operand. So here, if we see it actually is a multiply, okay. It's a multiply, then its precedence is higher, okay. And the next token actually is identifier, okay. Identifier. So the precedence is the precedence of the temp and the token. Temp is the top of the stack, is this one, okay. And then token is actually the current token coming in, okay. So it may be a multiply. So multiply is higher, okay. In that case, we will push in that multiplier. Okay, we'll push in multiplier. Okay. If actually it is not, okay, if it is actually not, then what? Then we will pick. Okay, we will actually pick the top one, we push it and pop one, and then the new template. Then new temp will be this one. Okay, new temp is this one. Okay, and then anyway, we are going to push in the token to it. Okay, we'll push in the token to it. So here we have a plus sign. Okay, here we have a plus sign. Okay, so here actually, if our plus sign actually is of higher presence, and we will pop out right away. Okay, we will pop out right away. So in this case, this multiply will not go in. Okay, multiply will not go in, and we will see a parenthesis. Parenthesis is lower priority. So we see a B will be assigned, and D will be assigned. Okay, then we see a parenthesis that's lower priority. That's a lower priority. Lower priority, then we pop out the plus sign. Okay, we'll pop out the plus sign. Okay, so we will finish in this way. Then the next one we see so these two got pop out. Okay, this one we actually push in this multiply. And then we push in the parenthesis. And then we add the C to here. Then we add a C to here. Then we push in minus sign. And then we push in D, and right parenthesis is lower. So we'll pop out these two things and then put the minus sign over here. Okay. And then here actually we finish it. So we will pop out this star sign over here. Okay. That's the final pop out. Okay. And this will convert from infix to the postfix. Okay. So there's is identifier check. Okay, it's identifier check. So Python's string function check is string is a valid ID format. Okay, this one is tokenization. So you basically use the tokenization rule to check if the symbol is a valid ID or not. Okay, so that you can write a program to check if it's valid ID. Valid ID is not hard to check. You start with A to G, and underline. These are the acceptable symbols. Okay, the acceptable symbols. So you can write program or a regular expression to check it. Okay, and to string function is to convert infix to string function. It actually convert the whole items to a string. Okay, you press one by one. Now, let's look at this conversion of expression in a more systematic way. Let's look at conversion of infix expression to prefix and the postfix expressions. So fully parenthesized expression. So far, we have used the ad hoc method to convert between infix expression and the equivalent postfix and the prefix expression notation. As you might expect, they are algorithmic way to perform the conversion. So here we are going to introduce it more systematically. The first technique we will consider use the notion of fully parenthesized expression that was discussed earlier. Recall that A plus B times C can be written as parenthesis A plus parenthesis B times C parenthesis to show explicitly the multiplication has a precedence over the addition. On closer observation, however, you can see that each parenthesis pair also denote the beginning and the end of the operand pair with the corresponding operator in the middle. So operand, operator, operand, that organization is there. And infix to postfix. So look at the right parenthesis that is the ending of the B times C, okay, for example. So here we will have to decide, okay. So here if this one is of lower priority, not higher priority, then your plus sign should be, you should have what? You should have B, C plus, okay? And here you have parentheses, so you will actually form this, okay? If you don't have a parenthesis and you have A times B plus C, you really will make this one as AB time and then C plus, okay? So that is actually different, okay? That actually is different. The precedence of the operator actually matters, okay? The precedence of operator really matters. Okay, so if we do the same thing, instead of moving the symbols to the position of the right parentheses, and we get the prefix notation. So here we can change it to A, okay, times BC. Times BC is once you move the operator here, okay, and you move the plus to here, then you become your the so-called prefix operation, okay. Okay, systematical conversion. In order to convert an expression, no matter how complex, or either prefix or postfix notation, fully parenthesize the expression using the order of operation, then move the enclosed operator to the position of either the left or the right parenthesis, depending on the prefix or postfix. Okay, that's the systematical way to do it. So basically, whenever you finish a parenthesis pair, you decided to move the operator to be here or to be here. Okay, that's the way, that's a systematical way we talk about here. Okay, but before you do that, you actually need to fully parenthesize your expression from the non-fully parenthesized one. Okay, so first one, infix to postfix. Okay, so this one we already discussed the algorithm before. Okay, we have one example. Now let's consider again the expression A plus B times C. Okay, so it only is to change the position of operators. Okay, so A, B, C stay in the same position, but you only need to move this one here and this one to here. Okay, so that's a change of the operation. So here, this one actually stack is useful for the storage of operands. Okay, so you look at one A over here. Okay, and then you will see, okay, the order of the ABC is the same, so you actually put it in an array, okay, a list, and you push in your plus sign, okay, and then you put in your B, okay, and you put in your multiply sign, and then you put in your C, and then this one you actually pop this one out, and then pop this two out, and you should get your B, C time, and this value and A, okay, you put your B, C time over here, okay, and you actually pop out this two, and with this one you get A, B, C time and plus, okay. That will give you the solution, okay. So stack will help to do the conversion. So since the addition comes before the multiplication operator has a lower precedence, it need to appear after the multiplication is used, okay. So deal with parentheses. So here we have such parentheses, then we will actually pop out AP plus first before we pop out C times, okay. So that's that. So again, processing this infix expression from left to right, we see plus first, okay. In this case, we will see plus and then already press in there, okay. And we use this parenthesis to determine that, okay, it actually already finished the operation. Don't wait for another operator, okay. So that actually is that. So we can now start to see how the conversion algorithm works. Okay, when we see the left parenthesis, we will save it to denote that another operand of higher precedence will be coming. Okay, and then the operator will need to wait until the corresponding right parenthesis to denote its position. So right parenthesis happen, or you have the time operator come. Okay, you can determine whether you should pop out your plus sign or not. If it is a multiply sign, then you don't pop out. It's a parenthesis sign, then you will pop out. Okay. Okay. So create an empty stack called operator stack. Okay, to keep the operators, and then create an empty list for the output. Okay, for the output. Convert the input infix string to a list using the string method split. Okay, so tokenize them, and then scan the token list from left to right. If the token is an operand, append it to the end of the output list. Okay, if the parenthesis is a right parenthesis, then push a left parenthesis, then push to the stack. If the parenthesis is right parenthesis, then pop the stack until the corresponding left parenthesis is removed. Okay, so pop out until you have everything there. Okay, if a token is an operator, okay, times this one, you push it into the stack. Okay, however, the first removal of any operator already first remove any operator in the up stack that have higher or equal precedence. Okay, so you may pop them out if it actually is of higher precedence. So here, for example, you have a, okay, here you have a time and you try to push plus in. That means you try to push the plus in, means that this time need to be finished first, because you would have A times B plus C. So you need to pop them out, okay, before you push in the plus sign in the step and waiting for C to come and then pop out your operator. Okay, and then pop out your operator. Okay, so here is stack and parentheses. So we have A times B plus C times D. Okay, so initially we have empty stack and we add A to the output list. Okay, and star will push in. Okay, and then we see a B, so B put there, and then star come. Okay, star come, and then actually we see a plus sign. So plus sign is actually of lower priority. So we pop out star, and then we push in plus. Okay, we see a C, so push C on the output. And then we see another star. So star actually higher priority than plus sign. So we will let star stay. And we see a D, we drop it. And it is the end of the expression. So we pop out a star and then pop out the star plus. Okay, we'll finish that to convert it to from the so-called infix to postfix. Okay. So this one you still need to have a one stack, okay, and you need to assign your precedence of the functions, okay, of the operators, and you create an operator stack and output list, okay, and you convert your the string to tokens, and then every time you check the tokens, whether it's actually a number or a variable, okay, and you actually if it's number or variable, you add it to the output list. If it's left parenthesis, you push it. If it's right parenthesis, you pop out. You pop out means that you are going to pop out everything until you see a left side parenthesis. Okay, so keep doing that, and pop out thing will be added to your output list. Okay, and if it is not, if actually it is not left right a parenthesis and not a number available, then that's an operator. So you check if the stack is empty. Okay, if not empty, and also you pick that actually your top operator and the current operator. Okay, top operator and current operator. Top operator is of higher higher precedence. Then you pop out the operator. Okay, you keep doing that until this one is lower than your priority or the stack is empty. Then you push in your token. Okay, then you push in your token. And then when you see the whole stack being pushed or pop, okay, and you continue to, and you may not have the closing parentheses, so you need to pop out everything from your stack at the very end, okay, at the very end. That means to pop out all of your operators just like this one, you pop out all the operators at the very end. Okay. Okay, that is one example, and we operate on this different example, and they get the good result. Okay. So measure 2, postfix evaluation. So we do this one. It is what? It is the so-called building the conversion from infix to postfix. But postfix list, we can use it for evaluation. Okay, so we can use it for evaluation. So we do have, we do use the postfix list. So let's assume that we do have this one called 4, 5, 6 star plus. Okay, so we push in our 4 to the stack, push in 5, push in 6. We see a star, so we see a star. We pop out 5 and 6, multiply them, you get 30, and then we pop out these 2, we add in 30, and then we see a plus sign now. So you pop out these 2 values, and then we get 4 times 30, and you actually get 120, and push into your stack. So there's only one data and no more operand, so that the value will stay at the bottom of your stack. Okay, that will be the evaluation. Okay, that's how evaluation been done. Okay, so been done. So here we push 4 in, push 5 in, push 6 in. We see a multiply. So we pop out 5 and 6, multiply them, and push back 30. And then we actually continue. Okay, this one is plus. Okay, I'm sorry. Last time I used a multiply to make it 120, so it's wrong. So here we pop out these 2 and plus together, it becomes 34. Okay. Okay, that's a postfix evaluation. So this shows you that postfix notation is very good. When we use a single step, we can evaluate the expression. Okay, so basically what we learn over here is you may have infix notation, you convert it to postfix. And postfix is suitable for evaluation. So basically this one, you tokenize them into infix list. You convert it to postfix, and then you do evaluation. Okay, and then you do evaluation. So that's good idea. So if you can convert things to postfix, then you will be able to operate the evaluation. So here we push in 7, push in 8, we have plus sign, we pop them out, so we get 15, and then we push in 15, and then we actually push in 3, push in 2, we have plus sign, we pop out 3 and 2, and then sum them together beyond 5, push in, and then we see a division, so we pop them out, 15 divided by 5, it becomes 3. Okay, that's the evaluation. So that's the algorithm for evaluation of expressions. So here we do have a simple program. Okay, you see a expression, you create a stack. Okay, you have a token list. Okay, create a token list. So if the token is in here, the number. Okay, then you push it. Okay, you push the token to the stack. Okay, and the operand stack. Okay, and if you actually it is not the number. If not the number, then we actually will pop them out. Okay, pop them out for 2 operands, and then operate the token to the operator to the 2 operands, and then push back the result. Okay, push back the result, and we keep doing that. Okay, keep doing that until all token being done. Okay, all token being done, that you will have the last value, and you pop out the last value, that will be your result. Okay, so here we have some question. Okay, we may have some variables such as A or 125. Okay, this example only use 0 to 10, so you need to qualify the value. Okay, qualify the value if it is not this one. If it is not a single digit number, you can change it to the evaluation of this. And if it is available, you can replace it by using a simple table, and the simple table may have value. Okay, and use that. when you deal with the evaluation. Okay. And in the middle, you you may assign value. You can change your symbol table. Okay. So that's that. Okay, so this one 7A plus. So push in 7, push in A, pop out 7 and A plus, they become 15. Push in 3, push in 2. Okay, pop out 3 and 2, and push in plus together, push in 5, and then pop out is 2, and then do division, you get 3. Okay. So postfix to infix conversion. Okay. So conversion of the postfix expression to a infix expression. Okay. So you read the postfix expression from left to the right. Okay. If the symbol is an operand, then you insert it to the front of the queue. If the symbol is a operator, okay, you pop out 2 symbols together and then put the 2 value into your output list, okay, and then insert the operator in the middle, okay. So this one is the way that you actually convert postfix expression into an infix expression. So let's look at this one. You look a, you directly put it in here, okay. You put C B, okay. You actually put it in here, okay. So next one you see a minus, right? You pop them out, and then you create this and push into your infix expression, okay. Then you see a C, okay, see a C and D, okay, you put them in, and then you see a time, okay, and then you pop them out, okay, and then you time them together, okay, and you push them back to the head, okay, so you have this one and this one. Then you see another one called plus sign, you pop them both out and insert this one. Remember, this one push and pop doesn't happen on the tail, it happens on the head, okay, it happens on the head. So this one is the way that you convert your postfix to infix. But remember, the push and pop now actually is at the head, okay, not at the tail side. So here we have a postfix expression, and we have a result S, okay, result S array. So now we actually try to figure out how long it is, and then each one of them we get a see if it's an operand, okay. If it is an operand, we insert it to the front of the stack of the queue, okay, of the queue. It's not stack now. And then if not, okay, if not, then I think it is a operator. So you pop out 2 operator and actually pop out 2 operand, okay, pop out 2 operand, and then you insert the parenthesis with 2 operand and the infix the operator in the middle, okay, insert it to the front, okay, and you finish, you take out the whole thing, and that one is a string that you want to have, okay, is here. So this one is the conversion of the so-called postfix to infix, okay. This one is prefix to infix, okay. Prefix to infix, okay, you read the prefix thing, okay, left, right to left, okay. So if it's an operand, you push it to the stack, okay. If it is operator, then you actually pop 2 symbols from the stack, okay, created as a string by pressing the operator in the middle, okay. So here you need to do it from right to left, okay. That's the only thing you need to know. Otherwise, it's similar to your postfix one, okay. So here we have plus A, B, star, C, D. So that's actually start with D. So D push in, C push in, okay, pop them out, okay, and then time together, you get this and insert it in, okay. The next one you see a B, push it in, see a A, you push it in, and then see a minus, you pop them out and insert it there, okay. And then you see a plus, you pop both them out, and then you actually sum them up, okay. So this one will get it. Remember that your operand is left, okay. You write first, so write first, you have a new one, that one should be on the left, okay. So when you create the so-called result, okay, you should put your second operand in front, okay, because we are doing the scanning from right to left, okay, we're doing the scanning from right to left. Okay, so that is the way we do it, okay. You can check this algorithm, okay. You can check this algorithm. Next one, prefix to postscript conversion, okay. Prefix to postscript conversion, we read the prefix expression from right to left, okay. If symbol is operand, we push it to the stack, okay. If the symbol is an operator, we actually pop the two symbol out and then insert it back to the postscript format, okay. So we do the similar thing. We see a D, okay, and we see a C, okay, and we create CD, okay. The only difference of this one from prefix to infix and prefix to postscript is the generation of the postscript format, okay. And you put in your B, put in your A, convert them to AB minus, okay, and then you pop out your AB minus and the CD times, okay, and it's a plus, okay. So this way, and the previous one, the so-called postscript to infix is similar. So postscript can be used to convert it to infix, okay, infix, okay. Okay, and this one is prefix converted to infix, okay. And this one is a prefix converted to postscript, okay. These two are very similar, okay. Okay, summary. Okay, summary. It is important to know that both prefix conversion and the postscript evaluation program, we assume that there were no error in the input expression. So if there are errors such as the parentheses not match or something like that, you have to deal with it. Okay, and there are also some issues such as the string are not fully parenthesized. Okay, in that case, you need to deal with the parentheses first. Okay. Okay, so this one is a starting point, okay? And actually, stack can be used for maze, okay? So backtracking. And backtracking is used for the so-called recursive descent operation, okay? So here we teach you how to deal with the evaluation tree, also the stack and also the infix, postfix, and prefix conversion. Is very important for the language processing, okay, if you use the stack to deal with them. So syntax tree, stack, and the evaluation, okay. So here in this lecture, we briefly go over the functional programming and its relationship with recursion, okay. Then we work on the tree construction and the various type of tree, okay. We talk about tree, and one of them we call it parsing tree, okay, and parsing tree, and we also do evaluation on the postscript, okay, and we also talk about the conversion of different expressions, okay. So here, this one, okay, this one we actually can pass. We can pass 1 plus 3 plus 5 plus 7, okay. We can pass them. And you can pass it, okay. Every time we see a plus sign, okay, we actually put them together, and then we actually get another operand. We put it, so we get this result, okay. This so-called parsing tree. Parsing tree is our syntax tree, is our expression tree, okay. In the tree type, we talk about it here, okay. It's the expression tree. Okay, that's the expression tree. Okay, but your tree may, okay, same expression, you may end up with right first, okay, right first or left first passing tree. You may have ambiguity in terms of different tree, okay. So this chapter, let me actually summarize it in another way, okay. So basically we have input string and we need to tokenize them. So we have A plus, okay, B and then plus C. So we tokenize them, okay, we actually tokenize them. Okay, then we want to build this one into a passing tree. So this one we call it syntax tree. So we need to know about the tree structure and how to build a tree. Okay, and while we deal with this different thing, we actually need to use recursion. Okay, recursive function, and also functional programming. Okay, and we also show you when we build a tree, we have different format conversion. So this one is showing you the functional programming and its application to the syntax tree, and also including the evaluation of syntax tree if you know how to do postfix expression, and you can directly evaluate on that. Okay, so that's the main idea of this chapter, is to teach you the overall solution of the evaluation tree and build a tree, and you can also evaluate it and use the functional programming way to do it. Okay, thank you. Bye now.